So I have about 10 more lectures to go, and I want to head in the direction of non-singular algebraic, non-singular projective algebraic curves. And the Riemann-Roch theorem. So this is a kind of big part of mathematical culture. What I'll talk about, was understood around 1860 by Riemann, but has been developed very much. And the treatment I'm going to give is really owes a lot to 20th century ideas. So the picture is I've got C in Pn, so it's going to be given by a lot of equations. I have to do the background to it. We can talk about functions on C. So this is the function field. So I'm working over a field K, and for most purposes, e.g. K equals C. So for most purposes, I'm going to say that my C will be algebraically closed, and in one or two places it's convenient, but not essential to assume. So I want or K algebraically closed. So there's a function field, and then if I say I fix P1 up to Pn in C, let's say P1 up to Pk in C and N1 up to Nk in Z, let's say greater than 0, then I'm going to talk about L of some NIPI. So this is the space of rational functions on C with pole less than or equal to. Okay, so I'm just giving you an indication of what the general idea is. So later on, this is going to be called a divisor. So here's my curve, right? Or you can draw it like this if you like, because if you're over the complexes, you can draw the curve like this. And then here's some points. These are pi, and then d is sigma NIPI. And so, the theorem is that this is a finite dimensional vector space, and its dimension is L of D is L of D. And this is greater than or equal to 1 minus G plus the degree of D. So this is plus some Ni. And often equal. Right? So Riemann's work on this is around 1860. Okay, so this is a big result in algebraic geometry. It's basically the beginning of systematic study of the algebraic thing. So there's this G equals G of C is the genus. So the word genus has some kind of biological connotation. In biology, you have genus is a kind of big family, and then species inside it is a smaller family. So in any case, here at the time of Riemann was 1 or 2 years after the publication of The Origin of Species by Charles Darwin. So terms from biology were sort of popular in science at the time. Right, so in any case, this is a property of a curve C, and in the picture it's the number of holes. It's a topological. Okay, so you know there's something really very remarkable going on here. So I'm doing algebraic geometry, so I write down a finite number of polynomials that determine some subvariety, and later on that subvariety is going to have dimension 1 and be a non-singular curve. On the other hand, over the complex numbers, I can write down this thing, and I get this thing is the picture I'm drawing here is a Riemann surface. And so the Riemann surface has complex analysis on it. It has functions of one complex variable. So if I take any place here, if I take any neighborhood, this is like this is holomorphically isomorphic to the disk in C. And so this thing is a Riemann surface, or a one-dimensional complex manifold, and on it you can do analysis. So I'm going to really be talking about algebraic geometry, but these are also spaces of meromorphic functions. So L of D is a space of meromorphic functions, meaning that if I look at them locally in any neighborhood, then I've got a one complex variable, and these things are meromorphic functions of that one complex variable. Right? And so this the number this thing here is this space of meromorphic functions. So this is so L of D and L of D. So L of D is a vector space, and this is its dimension. Right? And so this is, if you can think of this as being analysis, you can think about how many globally defined meromorphic functions there are. Right? But on the other hand, the thing on the right is really topology. The G is this picture, how many holes, and the degree is how many poles we allow. So in the neighborhood of a pole, in the neighborhood of one of these points pi, I allow the meromorphic function to have a pole of order 1, but you can think of that as being something to do with curve wrapping n times around at that point. You can think of the right-hand side as being topology and the left-hand side as being analysis. You can also think of the whole thing as happening inside field extension, so happening inside the framework of Galois theory. So this is the aim. So in doing this, so this is the thing I've been doing here is the overall aim, right? And there are a lot of technical things to do. So I still have to define projective variety. So still to define in preparation. So I have projective variety. I have the the coordinate, projective coordinate ring, homogeneous coordinate ring. I have the local ring. So I have defined this, but in a slightly different context. So if I take a point P in C, I want to say that a neighbourhood of the curve P in C looks like a complex disk around P, and so I want to say zeros and poles. Right, so I need this local ring and its properties. Right, and then there's several other things associated with this degree. Etc. In particular, if C is in Pn, there is the degree of C, which is the number of points in a general hyperplane section. Right, so here's my C in Pn. In there I take Pn minus 1, and I call this H. And I think of this H as moving around as, and then C intersect H is the hyperplane section. And you know, the thing I want is that this meets the curve C in the number of points equals degree C. Right? And you know, the thing that's not completely obvious is that if I took a different plane, maybe it would meet in a different number of points. And so this is really the problem which I mentioned earlier of earlier I didn't give a proper proof of Bezout's theorem. So this is related to, I mean, I'm not going to say exactly how it's related, but this is related to Bezout's theorem. So the question is really, why is this degree well defined? Okay, so I'm an algebraic geometer, and all the time we're doing, rings of functions, coordinate rings. There's this thing called the homogeneous coordinate ring. And it's really very convenient to be able to say that this degree is not this geometric thing. It's not this picture which a topologist will understand, but it's something to do with this homogeneous coordinate ring and these local rings. So that's part of the preliminaries before we can even start on the proof of on the statement and the proof of Riemann-Roch. Okay. So this is I'm giving you this. These lectures are sort of rather concentrated. There are 6 lectures this week and 2 immediately following. So I'm giving you a warning that the material I want to talk about is not really contained in the undergraduate algebraic geometry textbook. So the person taking notes will have to fill in stuff from the lectures. Okay, so let me go back to where we start from. So the I gave lectures over about 6 weeks already, covering essentially the beginning and the middle half, the middle section of UAG. So so I've got K, an algebraic closed field, and I've got x in an over k. So this is I want to say irreducible algebraic variety. Right. So the thing we immediately get from this is this ring, which is called kx, which is k of x1 up to xn, and then divided out by the ideal Ix. Right. So the x1 up to these are coordinates on the space. So I take all the functions that are polynomials on the space, and then I think of them only taking their value on x. So dividing out by Ix is saying that two functions are equal if their difference is 0 everywhere on x. Right. So this is polynomial functions on x, and this is so in the material so far this has been called the coordinate ring of x, right? And from now on I want to call it the affine coordinate ring of x, right? Because there's also going to be a projective coordinate ring. There's also going to be this homogeneous coordinate ring. Right. So let me just remind you. So there's this the main results. So this is towards proposition 4.4 in the textbook is saying that x and k of x are the same thing. Right. So of course this is a completely crazy statement, but what the proposition says is if I've got a variety, irreducible algebraic variety, in affine space, then I get this ring k of x. And conversely, so this means x goes to k of x. So this is a certain construction. And then there's a certain construction that goes backwards. So k of x goes backwards there. So here, this means take generators of k of x. So x1 up to xn is one set of generators, but this is a ring. It may have lots and lots of other sets of generators. So and where in geometry you don't choose coordinates in advance. Coordinates are something that you can make transformations, and here we're allowed to make any polynomial transformations. So this is corresponding taking any functions in here as possible generators of this ring, right? And then find the ideal of relations between these generators, right? And then define x is v of this ideal. So I'm sort of reminding you in rough terms of what I do. So the main result, as I said, this proposition 4.4 saying that there's a equivalence, so contravariant equivalence of categories between affine algebraic varieties x and so geometric K algebra K of x. Yes. So just to give a sort of basically trivial example, I mean, it's trivial, but it's useful for what I want to say. So here is A1 in a variable t. So this is just the ordinary line over the field K. It might be the complex line. And then I'm mapping this forward into, I'm going to do this. You know, nothing very difficult here. I'm going to set x equals t and y equals t squared. Okay, so the thing I've got here is gamma inside A2, x and y, and it's of course given by y equals x squared. It's just the image of, it's the image of this map. So this map's an isomorphism. So it's an isomorphism because given this thing I can just forget the y. Y is a function of x, so I can just forget y. Right? But so I have this ring here which is k of x, y divided out by the single relation y equals x squared, y minus x squared, and this is actually isomorphic to k of t. Right, so you know, there's some kind of geometry going on. This thing's called a parabola and so on, and studied in various contexts other people. So you know, when the Greeks said parabola, they weren't thinking of it as a variety up to projective equivalence. They were thinking of it as some shape occurring in the real world. Okay, so that was the good story, the story about affine space. So x in Pn, I want to emphasize this point. X in Pn is completely different. So there's going to be something called homogeneous coordinate ring. There's going to be you know, some algebra and so on. But it's not true that there's a simple equivalence of categories between the varieties and the algebra. The relation between the geometry and the algebra is sort of more complicated than that. Right, and so just to give an example, a trivial example, but an example that illustrates, you know, that explains why I said this. So here's P1 with homogeneous coordinates, let's say U0, U1. Right, and then as you all know, I can map this isomorphically into Q in P2. And this is just isomorphism, Q in P2, where this is, you know, let me have coordinates UV here. And let's map this to U squared UV V squared. And so call these x, y, z, and then I have x, z equals y squared. Right? So, I mean, we've discussed this at length already. This, you know, this is, I'm in the x, y, z plane. I have some picture like this. So this is in P2 of x, y, z. Right. So if you want to make a ring, if you want to associate a ring with this variety, then what you're going to write is k of uv. Right? If you want to write a ring, if you want to associate a ring with this variety, you might write down k of x, y, z divided by x, z equals y squared. X, z minus y squared if you want to see. Ideal, a principal ideal generated by this. Right? So the geometric locus here, P1, is isomorphic to this non-singular conic curve. But if I take their homogeneous coordinate rings, I mean, they're certainly not isomorphic. So they're, you know, certainly not isomorphic. Right. So there will be a relation when I've set up. There will be relations, but so and the reason is clear. So P1 is the projectivization of K2, so it's I'm taking K2 minus the origin, whereas so Q is the projectivization of the cone xz equals y squared in P of K3. Right? So when I write these rings here, when I write these things which are later on going to be called the homogeneous coordinate rings, these things are not just not a property of the variety, but properties of this cone over the variety. So it's time to give sort of better definitions, more straightforward definitions. So so let me do this. So this is a warning that when I start doing the foundations of projective geometry, projective algebraic geometry, you know, it's sort of all built on the same ideas, using the same language as the affine case, but in substance it's really quite different, and you have to be quite careful about it. Okay. So let me start doing with this projective version of the Nullstellensatz. Okay, so I'm going to go from so I want to talk about varieties in Pn. So consider K of x0 up to xn. So this is the projective coordinate ring of Pn. Right? So what is the structure that this has? So this is really, so together with saying affine coordinate ring here, I'm also going to write K affine of x. Right, to warn you that we're not talking, if x, you know, sometimes just to remove the ambiguity, x might be projective variety. So this is K projective, the projective coordinate ring, and this is K affine of K n plus 1. Right, the Pn is K n plus 1 minus the origin, and then divided out by an equivalence relation. And so this ring here, this is a ring, but it's also homogeneous. Right? Or it's graded. So you know, these two words are sort of they're going to be used more or less interchangeably. So what's a graded ring or a homogeneous ring? So I've got a ring R, and I'm going to write R is direct sum R n greater than or equal to 0. So R is so the thing I'm defining is a graded ring, right? Defined to be a ring with this decomposition. Right. So what are each of the RNs? Each of the RNs is a sub. The Rn inside R is a vector space. Actually, I don't. What do I want to say? So you know the Rn for the moment. Let's just say is a additive group. Is a subgroup. It's enough to have subgroup. So it's an additive subgroup, and then when I do multiplication, and the multiplication of the ring, and the multiplication in R does Rn times Rm is contained in Rn plus m. Okay, so what am I talking about? Well, if I've got a polynomial in x0 up to xn, I can take the polynomial and I can write it as a sum of homogeneous pieces of different degrees. Right? And so that's this statement. Any element in the ring can be written as a direct sum of elements of homogeneous polynomials of different degrees n. So I can take any polynomial and I can chop him up into pieces which are homogeneous of the degree n. And the guys that are polynomials that are homogeneous of degree n obviously form a subgroup. If I take the sum and the difference of homogeneous polynomials, they're still homogeneous. And then if I multiply the two guys together, then the homogeneous degrees just add up. Right? So this is really the key point, that we're going to do all of this algebraic geometry correspondence. I'm going to start talking about the definition of subvarieties and the ideals corresponding to subvarieties, but we're not, together with the fact that I have not affine space but projective space, I'm going to be working with rings and ideals that are homogeneous or graded. Okay, so I gave a kind of very general definition over there. In our case, I have k of x0 up to xn, and then maybe divided out by some j, and then so let me just leave it at this, corresponding to Pn. So if I've got an ideal in there, ideal J is homogeneous, or again we could say graded, but I tend to say graded ring and homogeneous ideal. So you know, this ring already has this structure of graded ring over there. So the ideal is homogeneous if any f in J can be written as f equals some fi with I in greater than 0, greater than or equal to 0, and each fi homogeneous of degree I. Right? So this is just another way of saying that if I take this J is contained in this ring R, which is the direct sum of Rn, if I take any element f in there, then this f is a direct sum of elements in, so this is a sum of elements in J intersect Rn. Right? So that's the same as saying So this condition just means that J is the direct sum of Jn, where Jn is J intersect Rn. Okay, so you know, if I write down f is x squared plus y cubed, right? This is not homogeneous, right? So if I want to, if I take the ideal J, which is just the principal ideal generated by x squared plus y cubed, it is not homogeneous ideal. Right, it's not homogeneous because I take the element, I take this f. If I write him as x squared plus y cubed, then these are not actually in J. That breaking up into homogeneous ideals, breaking up into homogeneous pieces of the same degree does not preserve belonging to the ideal. So on the other hand, if I write J is x squared and y cubed, this is homogeneous. Right? Well, this is of course a bigger ideal. This contains this one, but x squared and y cubed are not sorry. J2. Okay, so this is just a definition. So when I do the Nullstellensatz for projective varieties, I'm going to be working on with homogeneous ideals on the one hand, and then subvarieties of Pn on the other hand. Okay, so why graded homogeneous? So there's a little lemma here. That if let's say, let me take V vector space over an infinite field. Then a grading of V is direct sum Vn. Let me say now n in Z is the same thing as, so grading is the same thing as an action of the multiplicative group. So if I call this K, multiplicative group. So let me write GM, or K multiplicative. So you know, why have I suddenly started talking about graded rings? Well, I told you earlier that projective space is Kn plus 1 divided out by an equivalence relation. And this equivalence relation is an action, this equivalence relation is an action of the group K star. Right? This is just a completely basic thing in lots of different areas of mathematics and you know, of algebra and geometry. What do I mean by this? So if V so if V is direct sum of Vn, n in Z, then I can make Gm act by lambda in Gm. Lambda in Gm is lambda to the n on Vn. Right, and conversely, if V is a representation of Gm, then I can take the lambda to the n eigenspaces right, as Vn. So, in other words, I'm saying that, you know, why am I interested in homogeneous polynomials? So, the basic thing I'm saying is that a polynomial f of x0 up to xn is homogeneous of degree, let's say d, if and only if, when I do f of lambda x0, lambda x1, lambda xn, I get lambda to the power of d times f of x0 up to xn. Right? So, well, one way round this is obvious. You know, for example, if f is x0 to the power of d plus maybe, you know, x1 to the power of a, x2 to the power of d minus a, etc. I mean, you know, in general, with some coefficients here, it doesn't matter. Right? So this is what it means to say that if I take all of, so the general case is x1 to the x0 to the n0, x1 to the n1, and so on, n to the d0, d1, dn, the sum of dn equals d. Right, then when I do this lambda x0, I'm getting lambda x0 to the power of d, and that's lambda to the d times x0. Or here I'm getting lambda to the power of d0 plus d1 plus dn times x0, d0, x1 to d1. Yes? So, if the thing is homogeneous of degree the given d, then when I do f and I apply it to that, then I get, I'm just multiplying the polynomial by lambda to the d. So when I'm working with projective varieties, I'm only going to work with homogeneous polynomials, because then the question, is it true that f of p equals 0? The value of f of p is not defined, but the condition f of p equals 0 is defined. Okay? Now, so conversely, why is this true conversely? So suppose the polynomial has this property that when I do f of lambda to the d, you know, that substituting lambda xi for the xi gives me, just multiplies the polynomial by lambda to the d. Why is it true that then f is homogeneous? Well, break up f into, it's a proof of the if statements. So if f is you know, sum of f, yeah. Let me just say is if f is f of d plus f of e with two different terms, two different degrees, right? Then I do f of lambda x equals f is lambda to the d fd plus lambda to the e fe, and you know this. So, in other words, if the f has homogeneous terms of different degrees, then there'll be different exponents happening here. Right? So, in other words, the property of being homogeneous of degree d is the same as saying that we're in the lambda to the dth eigenspace or character space of the representation of the group C, GM acting on x0 up to xn. Okay, maybe I'm making this a bit too abstract. Right, so K star, this K multiplicative, the multiplicative group of the field acts on the polynomial ring K of x0 up to xn. And it's, at least if k is infinite, the eigenspaces are the homogeneous pieces, are the eigenspaces are the Rn. Right? So here I said, I start off with the ring, it's a homogeneous ring, and so on. But saying it's a homogeneous ring this is the same as an eigenspace decomposition for this multiplicative group action. And this multiplicative group action is the equivalence relation that defines projective space. So, sorry if it's a bit abstract, but it is really very basic mathematical idea. So I'm going to do, you know, I want to do this. I want to do ideals. Let me say, I'm telling you roughly what I want to do to subsets. So this is ideals of kx0 up to xn, and I'm going to go subsets of Pn. Right, and then I want to have a correspondence I going that way and a correspondence V going that way. And then I want to say same results as the affine. So like the affine Nullstellensatz. Okay, so what do I have to do? So I've already told you one of the little tricks. One of the tricks is here we're going to we only work with homogeneous ideals. Right, so that's one part of, you know, one ingredient that I have to throw in to this to make this cookery work. Right. So on the left-hand side, I only have homogeneous ideals. Now there is another little ingredient I also want to throw in. So let me say J. So I want that J does not contain x0 up to xn to some power m for any m. Okay, so what's this about? So I tell you, ideal in the ring. So so e.g., the ideal, you know, x0 to the power of, you know, m. Think m is 100. So if I take ideal x0 to the power of 100, x1 to the power of 100, and so on, xn to the power of 100. Right, and then I ask, what are the points of projective space on which all of these things vanish? Right, then V of J will be the empty set. Okay, because I'm going to be looking at points here. So I've got a point P is x0 up to xn, and then I'm going to be asking that f of P is 0 for f homogeneous in the ideal J. Okay, so I look in this ideal and I ask for some homogeneous elements. Well, here's one of them, x0 to the m. And so the points of this variety will all have x0 equals 0. So x0 to the m equals 0, but the value of, you know, the coordinate of the point is an element of a field. So saying that x0 to the m is 0 means that x0 itself is 0. So x0 is 0, and then x1 is 0, and then xn is 0. And that means that the point P is the point 0, 0, 0, 0, 0. And that's exactly excluded. That's not allowed in Pn. Okay? So this is a little, you know, there's nothing very clever here. I just have to avoid a trivial case. So if J contains x naught up to xn to some power m, then we say that J is irrelevant. So it's just traditional to say irrelevant ideals. Right? So, you know, I mean, here I was doing with something sensible. Here I was doing with this idea that we have to take account of the equivalence relation involved in defining Pn, and the equivalence relation is a group action, and so I have to take my polynomials to be sensible with respect to this group action. Here the second point I'm making here is just a trivial point, that I don't want to keep getting the empty set as the answer to the question of what is the variety of some ideal. Okay. So that's the preliminary thing. You know, all of this is just words. I mean, this is just definitions and really very, very elementary things. Eventually I'll say a theorem, and the proof will just be apply the affine Nullstellensatz. So this is inside P of n, and so this is the set of all points P, so this is you know, a naught to an in Pn, such that f of P, f of a naught up to an equals 0 for all f in J. Yes? So normally when I write this condition, this is the condition f of p equals 0, you know, I've told you several times that it's illegal to write f of a naught up to an, because a naught, so this is a choice, this guy here is in kn plus 1, you know, preferably minus the origin, and then but is only a representative of an equivalence class. So I'm allowed to multiply all the, but I could also have lambda a naught, lambda an. Right? It will be the same point of projective space. Right? And so it's not really legal to write this condition, f of p equals 0. On the other hand, the f is, for all f in J, all f homogeneous. Right? This J is a homogeneous ideal, which means among its generators there are homogeneous elements, or every element in J can be written as the sum of homogeneous elements still in J. Right? So if f is homogeneous, so NB, if f is homogeneous, then f of P, f of a naught up to an equals 0 is well defined. Now, so i.e. f of lambda a naught, lambda a n is lambda to the n times lambda to the d, homogeneous of degree d, times f of a naught up to an. So it doesn't matter if I'm asking for this guy to be 0. This one is 0 if and only if this one is 0. Right? Because I'm multiplying through by lambda, which is a non-zero element of the field. Okay. So that's just the definition of the. This is the correspondence V. So set V of J is a projective algebraic variety in Pn. Right, and then there's going to be a correspondence going the other way. I start off with some set in xn, and then I map this back to I of x. So who's I of x? So this I of x is a set, is the ideal generated by homogeneous ideals, homogeneous polynomials f with f at p equals 0 for p in x. Right. So you know, what do let me give an example. Sorry, when I give an example, they're not really very sensible examples, but maybe I can think of something. You know, if x is one of my favorite things is this curve gamma in P3 curve defined by let me take the gamma equals the image of P1 under u squared, u cubed, uv, u squared v, uv squared, u cubed. Right, so this is this rational normal curve that we've seen many times, rational normal cubic curve. Right, and so I go into this polynomial ring. So let me call this x, y, z, t. This is an example. Sorry, I'm putting the example together with the definition. So, e.g., example, if gamma equals the twisted cubic in P3, then we know, we work around for a little bit, and then we discover that the ideal of gamma contains, you know, whatever it is, x, z minus y squared, and xt minus y z, and x, t, y t minus z squared. Right, and then we can go into degree 3 and ask for all the homogeneous polynomials of degree 3 that vanish on it, and then degree 4 and degree 5 and so on. And you will discover eventually that, well, you'll discover, if you care to do this exercise, you'll discover that all the cubic forms that vanish on this curve are actually just already in the ideal generated. So these, these generate the ideal I of gamma. Okay, so just to make the definition, I'm starting off with a set in X in Pn. The set might not be an algebraic variety. It's just any set, right? And then I just ask for all the polynomials that vanish on it. Okay, so you know, it's very, very similar to what we did in the affine space. The only difference is that I have to keep taking account of this fact that f of p equals 0 might in principle depend on the particular choice of a naught up to an. So if the f is not homogeneous, then obviously the condition does depend on that. But as long as I stick to homogeneous polynomials, so this I of x is the ideal whose homogeneous pieces consist of homogeneous forms vanishing on P. Okay, so have I made sense? Are these definitions sensible? I think this is more or less what's written in UAG in any case. So let's do, let's say Nullstellensatz. So projective, not Nullstellensatz. So let's take J in k of x naught up to xn, a homogeneous ideal. Then the first thing is to say V of j is non-empty. So I'm going to say that slightly differently. I'm going to say V of j is empty if and only if j is irrelevant. Right. So I already said if I have an ideal like this, if I have an, so this is to say that xi to the power of m in j for all I. Right. So so the implication that way is obvious. If j is irrelevant, I gave the argument already. All of the xi's, all of the coordinates of projective space vanish on all the points. So the only possible point to be left is 0, 0, 0, but that's not a point of projective space, right? And then 2, if G is homogeneous polynomial, then G is in ideal of V of j if and only if G is in the radical of j. So this means i.e. G to some power m is in j. Okay, so this just gives us everything that the Nullstellensatz gave us for affine varieties, at least everything that's true. And the proof is just the proof. We'll just copy the affine proof. But applied to subvarieties in A n plus 1. Okay, so in other words, when I've got, so in other words, given J, I can do V of J in Pn, right? But I can also or I can do V affine of J in A n plus 1. So this is with coordinates x naught up to xn. So this is the thing, so I have to do affine n plus 1 minus the origin, and then I have to divide out by the action of k multiplicative. to Pn. Okay, so how are these two guys related? So V f of j is invariance under this K star action. Right? So that's the point that I've already written down several times. So in other words, if I've got A naught up to AN, right, and I do F of A naught up to AN, or I can do F of lambda A naught up to lambda AN. So I can make the K multiplicative act there, and then I get, the same thing up to this lambda to the power of d. So I'm writing down condition that polynomial equals 0. So that's saying that this guy is 0 if and only if this guy is 0. Right? And that's saying that so when I write down this Vf, I've got some, here is, Vf of j. Right? And here are these lines here are the K star action. The orbits of the K star action. So obviously the origin is a little bit special here. If this is the origin, then the origin doesn't go anywhere. Okay, so let's look at the proof of the first part. I say the variety in projective space equals 0, equals the empty set. The proof of 1. Right, V of j is the empty set. Right, this means that V of f of j is contained in. So it's a subset of this an. It's a subset of this an plus 1, with the property that if I delete 0 and then take its K star action, I get the empty set. Right, and that means it's the empty set here. And that means that all of this is contained in the set 0. Right? And then by the affine Nullstellensatz, the affine Nullstellensatz says this happens if and only if J contains the maximal ideal. It's x naught up to xn to the power of n. Right? So this is a statement. This is a statement that when I take the variety, the affine variety defined by J in this an plus 1, I get nothing but the origin. Right? And so therefore if I take any of these x naughts, they vanish there, and so some power of them vanishes, belongs to the ideal J. Right? And then some power, if I take the maximum of these powers, then each of x naught up to xn to the power of m, and all monomials in them of sufficiently large degree, belong to J. Right? And so this is just a completely automatic use of the affine Nullstellensatz. Remember that I had to work for about 2 lectures to prove the affine Nullstellensatz. That's a substantial result. This is just a trivial application of it. Okay, and then the same is going to be true of the other guy. So suppose that now I hope I've stated this correctly. I think I probably want G not 0. Okay, if G is 0, then there's nothing to prove. Okay, it's probably true. Okay, so for the second part, proof of 2. So given J, I do V of J is in projective space. Right, at the same time I can do V of affine of J, and that's in A n plus 1. So G is homogeneous, and G is identically 0 on V of J in projective space. Right, so if V of J is the empty set, so if V of J is the empty set, then this is not a very strong condition. Right, then J contains x naught up to xm to some power m. And so if G is 0, then G is in J. If G is not equal to 0, then G is homogeneous. Could G be could G be 1? Yes, okay. Okay, I'm wrong. This J, assume that J is, let's assume here that V of J is not irrelevant. Right. Right, because otherwise, so if I take, let me give the proof before saying why I need that condition. Right, and so anyway, we don't have this. So V of J is not 0. So this means that V aff of J is not contained, is strictly bigger than, contains and is strictly bigger than 0. Right, it's not just the origin. Right, and then G is 0 on G is 0 on V f of J. Right. So it's 0 outside the origin because of this assumption that G is 0 on V of J. And then it's 0 on the origin because it's homogeneous of degree greater than 1. Right? And this means that, but again, by the affine Nullstellensatz, G to some power m belongs to J. Okay, so you notice that I sort of hesitated about this and eventually got it slightly wrong. If G is 1, that's homogeneous of degree 0, and it vanishes on V of x naught up to xn. Right. And so I did actually use the fact here that this is not the empty set. So this would not be true without this assumption, because G could be the homogeneous polynomial 1. So G is 1, and so if I ask a set of points where this vanishes, I get the empty set, but that's okay because this one is also the empty set. Okay, so you know, I mean, this is sort of very theoretical in a sense. easy or boring, depending on how you look at it. Okay, so in any case, most of this is still in UAG. Any problems with this?